The plan for today is I want to talk about this discussion board. I want to talk a little bit more about the psychrometric chart that we started working on yesterday. I want to talk a little bit about the lab that I had in yesterday, that I made available yesterday, and I want to talk a little bit about the lab that I'm going to make available today. Again, this is all stuff that can be done off campus because, again, this is a design term and it's basically paper-based. So I want to, and then we do have to begin two PowerPoints. One, unfortunately, folks, is on triangles. I can't avoid it. We have to talk about it. The other one is going over some of the material from Chapter 27. Okay, I am going to try to keep this in the hour and a half that we've been doing. I sort of like that time frame. I don't think it's too long for you guys, and it covers what I need to. Once again, the lecture videos that I share are very important, okay? We do get a report of who watches them, so when I look at discussion boards, I can usually tell why sometimes we're not getting the correct answers or what I'm looking for in terms of discussion and why I'm not. So, can everybody see my screen?
No.
You're having the same problem you've had with that black thing again?
No, I never had it. I'm just having it now. It's like a dark black screen.
Is anybody else actually able to see my screen? Okay, I got a yes. Okay. What I'm looking at, if you want to pull it up on your own, is I am in the discussion board with the two pictures. Okay? That's what I really want to talk about. It's that discussion board with the two pictures. And if you're getting a black screen that you've never had before, I do suggest you think about rebooting your iPad. That seems to be the solution in a lot of cases. And I know somebody doesn't have that solution. So, okay, two pictures on this screen. The one on the left is from my Testo test kit. It's two psychrometric probes that are in the return and supply airstream. The one on the right is the same house. Okay, it was a house, and if you look closely at the windowsill on this picture, and I'm not sure I could, let me pull this up a little bit in size. Okay, if you look closely at the windowsill around, okay, this window, you start seeing what appears to be some growth. That's mold. You see the blinds in the picture. But here's the thing. This house is at a 50.5 return air relative humidity. Okay, 50% relative humidity is where mold starts to grow. Okay, that's actually, I believe, in our reading material. So 50% relative humidity is the point mold will grow. Okay, I have a 66.3 relative humidity supply air. We talked about this yesterday, that the supply air can and should have a slightly higher relative humidity, but remember it has less grains of moisture. Remember that cooling process that I did on yesterday's psychrometric chart. Okay, return air is 66.4 degrees, supply air is 47.6. So that temperature split, if you take a look at the temperature split between the 66.4, it wasn't what I wanted. That's what I wanted. So if we look at the 66.4 minus 47.6, we have an 18-degree temperature split. And again, for those who haven't had a real chance to look at the chapter yet and look at some of the material, to find the difference, find what my air conditioner is cooling the air with sensible heat. I'm not even talking about latent heat. I'm talking about sensible heat. We take that 66.4 and we subtract 47.6. So our return air minus our supplied air. I come up with 18.8. Usually we go for about 15 is our magic number there. So the temperature split between return air and supply is usually about 15, can be less. It's not normally more, so this is a little high. Okay, but the key is we're gathering moisture. Now, a little bit about this house, okay, and that's something that I wanted to talk about, and it's not part of the discussion board, but just a little bit of a background. This house is a 576 square foot house. So when you look at this, we're going to use more and more pictures from this house as the course goes on, because it was such a great example I stumbled across about 2 weeks ago. But this house is only a 575 square foot house. It's a little matchbox house. Sits in Tampa, but it has a 2.5 ton air conditioner in it. Now, I'm not sure if some of you guys have looked at your own houses to see what type of air conditioners you have in there, but a 2.5 ton air conditioner can handle almost a 1,500 square foot house if the insulation is good. This guy has a 2.5 ton air conditioner in a 575 square foot house. So that right there is a problem, but what I wanted you to get was that my temperature split is a little high, return air relative humidity is a little bit high, and the really important part about this picture on the right is that we do have some biological growth here. Mold, okay, is growing on this picture. And you can actually, if you look closely at this picture, you can almost see run marks down the side of that window. And again, if you didn't know to look for it, that's fine. That wasn't really what I was looking for in the discussion board. What I was really looking for was somebody noticing that there was some growth here on the window. But there's actually moisture running down this window. The gentleman is, shall I say, lack of better terms, he's a pretty big recreational weed user. And this run mark down here is air residue. Let's just put it that way. So in terms of the discussion board, okay, why do we need to use the moisture content of the air? A couple of you guys gave me a really good answer, but the bottom line is we need to know that our systems are running properly. We need to be dehumidifying. If you don't measure it, you don't know. So it's sort of important to know. Why do we need to know about humidity? Because it's for the health and safety of the occupants. If your humidity is too high, you're going to start growing stuff like this, okay? If your humidity is too low, believe it or not, a lot of people will start having bloody noses in low humidity. Their skin dries out, especially the elderly, okay? And especially elderly who are on oxygen. They will really feel dry air. It does do damage to them. Who cares about how much air weighs? Well, every one of us should, because we're going into the HVAC trade. We're moving air. That's a primary portion of what we do. We move air. We have to know about the air we're moving. Why is the purpose top technicians have an understanding of air movement and humidity? Because it's what we do. I mean, you can fix the box, but the box might not be the problem. There might be other problems that go along with it. I mean, my air conditioning could be working perfectly, could be getting perfect temperature splits, could be getting perfect amperages, could be having perfect charge on the refrigerant side. Okay, that's why I care about knowing about air movement and humidity. Okay, two pictures below. The one on the left is pretty close. My temperature split is a little bit high, but again, I didn't expect really you guys to know that, but it's pretty close. The one on the right, yes, we have a problem here. We have mold growing on this window. Okay. Any questions on this discussion board question? You guys still with me?
Yes.
Barely.
Okay. So, just do me a favor, and if you haven't answered this discussion board with a reasonable post, please go in and post an answer. Put what I just talked about in your own words. Again, there's no right or wrong answer in these discussions, because if it's totally off base, I'll try to guide you back to where we need to be. When I'm talking about air, by the way, in this course, I'm never talking about anything within the refrigerant lines. Okay, I'm never talking about any air that can mix with refrigerants. So just be aware of that. I'm always talking about the surrounding air, the ambient air, whether or not it's the conditioned air in the house or the surrounding air outside. So I know somebody did post about air and refrigerant lines. You are correct on that, but that's not really the air I'm talking about. I'm talking about the air that we're conditioning, in other words, heating or cooling. So that's one of the things I wanted to talk about. Now, on our labs, okay, this was the lab that I asked you guys to do. You still have time to do it, okay? Basically, all you're doing is looking up these two numbers on the chart and finding these other numbers. Okay, so for example, we do the dry bulb, temperature of 70, wet bulb of 55. Okay, so I'm going to do that one real quick. I'm not going to do all of these because it's only fair that you guys give it a try. But so we have a dry bulb of 70, wet bulb of 55. So we find our 70 degree line, okay, which is right there. Okay, we find our wet bulb of 55. Okay, we have a cross, we meet in the middle right there. So what it's asking for where these two lines meet. What is the dew point? Now again, if you watched the videos last night, you will know that the dew point is using the same temperature as the same scale as my wet point bulb, but it's straight across. Okay, so dew point uses the same number as the wet bulb. Wet bulb is at an angle, but my dew point is straight across. So in this situation, the dew point is sort of halfway between 40 and 45. Okay, so my dew point, I would say, is about 43. Any questions on that number?
I put 40 in that. That's, close enough.
I'm fine with 40. Okay, you're close enough. What I want to see is that you're able to get into the right scale. You're fine on 40. I'm not going to take off for that. That's fine. Okay, so the next number we were looking for was grains of moisture per pound. Okay, grains of moisture per pound is right over here on the side. So if I extend this line across, okay, how many grains of moisture per pound do I have? 40. Okay, or 42, 43, it doesn't really matter. Again, just be in the correct range. So grains of moisture per pound is right there at 40. So next we have to find relative humidity. Relative humidity are these curved lines. Okay, we are very close to that 40 because I have a 50 that's marked and I have a 30 that's marked. The line between is a 40% relative humidity. I would take 40, I'd take 38. Okay, any place right in there. It's very tough on some of these charts to figure out exactly where you are. But I would take 40% relative humidity. Now, enthalpy, okay, is the scale over on the left, the ruler's off to the side. Sort of follows the same line as the wet bulb, okay? 23 works for me as enthalpy. Did anyone get another answer? Okay, so that is how you want to do this lab. Any questions on this lab? Okay, there's no questions. I'm going to make another lab available that I really want to talk to you guys about. I want to give some directions on this. Okay, do most of you in your toolkits got a toolkit, or I'm probably about half of you got the toolkit, the newer toolkit that has the yellow psychrometer in it. Some of you have the older toolkit. It all depends on when you enrolled, okay? The newer toolkits were a little bit more expensive because they had an extra tool in it. The old toolkits didn't have the extra tool, but you can still do what we need to do. Okay, you have a yellow tool in your toolkit. It's a sling psychrometer, okay, or a psychrometer. It's digital, actually. That tool will take wet bulb temperature, dry bulb temperature, and relative humidity. For those who do not have the psychrometer, okay, to get a wet bulb temperature, you take your meter, okay, it all has a temperature probe on it. You take your meter, you put a small piece of paper towel that's damp, not dripping water, just damp over the end of that meter, and you can take wet bulb temperature. Put it on there tight enough where you can move it around in the air to get some air patterns across it, okay, and just give it 5 minutes and you can take a wet bulb temperature. Now, obviously, you're not going to be able to do these rooms that we have laid out, that we basically have laid out here, okay? You're not going to be able to do those rooms. Pick 4 or 5 different, pick 4 different places in your house. Take some wet bulb temperature readings. Take a dry bulb temperature. You can use your psychrometric charts to take relative humidity, and then just step out on your porch and take a dry bulb and wet bulb temperature. Again, I don't care where, but I do need you guys to take some wet and dry bulb temperatures. Do you have any questions on that?
Yeah, repeat what you said because you cut off.
Okay, where did you lose me? Are you still with me? Hello?
Yes. Yes.
Okay. Where did I cut off on giving those directions? Okay. Again, I need you to use either your wet or dry bulb and take some temperature readings in 4 different places in your house and just outside, okay? Just cross these names out and just room and where you took it, okay? Wet bulb, dry bulb. If you do not have a psychrometer, that's the yellow tool, put a wet piece of paper towel over your temperature probe for your meter, okay? And just put it on there tight enough so you can swing it around a little bit. Calculate the relative humidity. You can use your psychrometric chart. And you remember we talked about the comfort range yesterday. I drew the triangle on your psychrometric chart. That's the comfort zone. Okay, is it within or outside comfort zone? So that's going to be the lab assignment that's going to be assigned for today. Then answer the questions and submit it. Okay? And in terms of number 2, all I'm basically looking for, I'm going to give you the answer for number 2. A sling psychrometer is basically the same as the paper towel on your meter lead. Why does it have to be swung around in the air? Because anything with a wet bulb temperature, I have to move air across. That's the reason why. I have to move air across it. Okay, and the rest of those answers are found in Chapter 27. Any questions on Lab 7? Okay. folks, I want to talk about triangles, okay? For those of you who are having video issues, this PowerPoint is on yesterday's module, okay? It's the design for the trigonometry thing. Don't let the word trigonometry scare you. All I want to do is talk about triangles. I really need to have a conversation about this because, again, roofs are part of the design portion. We got to talk about roofs. So, trigonometry is all we're going to do about. We're talking about triangles. I do need people who have background noise. Please mute yourself unless you are asking questions. Makes it difficult for other people. Okay. Okay, so trigonometry is the math we use to solve triangles. We want to be able to find the length of the three sides and the three angles. That's all we care about, okay? I'm really more worried about the length because the length allows me to calculate area and volume. And when we're dealing with heating and cooling, area and volume are the most important parts of it. Triangles are classified according to their angles and their sides. They're either obtuse, right angles, or acute angles. Triangles may be named after one of these three by the types of angles they have. Now again, a lot of you probably remember this stuff from high school and middle school math, but let's get everyone to the same page. Triangles by their sides fall into three groups: equilateral, isosceles, and scalene. Okay, an angle can range any place from 0 degrees, which is the starting point, to 360 degrees, which would be a complete rotation. In other words, circle is 360 degrees. An obtuse angle is greater than 90 degrees. If you look at the top picture, the angle is between 90 and 180. It's the dark line we're looking at. So the obtuse angle is greater than 90 degrees. An acute angle is less than 90 degrees. So if you're thinking a roof line, if you are in an attic looking up at a roof, granted this picture is upside down, okay, but you're basically dealing most of the time, unless it's very old construction, you're dealing with an obtuse angle. We rarely are looking at it inside of the roof with an acute angle. Okay, but if you're looking up at your roof from the attic, you're dealing with an obtuse angle. Okay, it's going to be greater than 90 degrees. If you're looking at your roof from the outside, like the front of the roof, okay, you're standing on the ground looking at the front of the roof, it's going to be an acute angle. Okay, because it's less than 90 degrees. Your roof lines usually looking at the front of the house don't go up straight at 90 degrees and they're not greater than. So the top one, looking up at the roof from the attic. The bottom one, looking at the front of the house. A right angle is exactly 90 degrees with the line perpendicular to each other. Your floor and your walls coming together better be right angles in the most part. Your ductwork, if you have forced air heating or cooling, the ductwork, if it's not round ductwork, it's rectangular. It better have right angles. So the small square drawn in the corner is the symbol of the right angle. When two lines form a right angle, they're said to be square because it's a perfect square down there in the corner. You'll see that on blueprints, by the way. Whenever they have a true right angle, you'll sometimes see them put in this square that shows it's a right angle. So again, a lot of triangles have right angles, okay? And if you put two of these triangles together to get what looks like a roof, you do have two right angles. One on one side, on the front of the house, one on the back of the house, in the center. Sort of important to start thinking about when you're looking at this from a construction standpoint. A triangle with a right angle is a right triangle. A triangle that does not have a right angle is an oblique triangle. Oblique triangles have two types, obtuse and acute. So again, we have two different, okay, we have the obtuse triangle that's over the 90 degrees, and you have acute triangles that's less than 90 degrees, okay, if it doesn't have a right angle. The primary characteristic of an obtuse triangle is that one angle is greater than 90 degrees. The sum of the three angles of any triangle is 180 degrees. In other words, if you add up all three corners of a triangle, you're going to get 180 degrees. If you take measurements of a house or a building that you're designing a system for, and you're taking measurements of a roof and you don't get 180 degrees, you've measured something incorrectly. HVAC salespeople are famous for this. Sometimes you'll get diagrams and sketches from salespeople who've gone out to sell a job who are required to take measurements and bring back to the shop for the designer in the shop to take a look at and to create ductwork, do load sizing and stuff like that. I can always tell when the designer didn't actually measure because they're going to give me an angle of a roof line that is not a 180 degree triangle. So that's always a sign something's wrong. A triangle will never have more than one 90 degree angle. Okay, you have to have three sides. You have three corners. So if more than one is a 90 degree angle, it's going to come over 180 degrees. If you have an obtuse triangle, like you're looking up at the attic, okay, and you're looking up at the peak of the roof, that's an obtuse triangle there. It's going to be over 90 degrees. But that means the other two angles must always be acute. They must be less than 90 degrees. And a triangle having all three angles less than 90 degrees is an acute triangle. But in all cases, the three angles have a sum of 180 degrees. You have to have 180 degrees in a triangle. You can't do it any other way. So you have different angles, 48 degrees, 28, 37, just to show different angles. Again, this can all be done with measurements or calculations. Triangles can be classified in a different manner. They can be classified by the relationship of their sides. They can be equilateral, isosceles, or scalene. An equilateral triangle has all sides and therefore all angles equal. Okay, this is the only type by angle that can fall into this classification. Equilateral triangle. Every side is going to have an equal measurement. Okay, all three angles are 60 degrees because they have a sum of 180. You can't do anything else. If all the sides are equal, the three angles have to be equal and they have to be 60 degrees. Now, this is a very steep roof, something you'd see like on a Swiss chalet sort of type of construction. Very steep roof. Angles it's going to be equal, but 60 degrees, designed like you see this probably up in Vermont where they want, or someplace in the Poconos where they want the snow to fall off these houses fast. An isosceles triangle has two equal sides and therefore equal angles. Okay, so if you have a right angle down at the bottom left of this, you can tell by the little square down at the bottom, okay, your other two angles have to be equal. The sum of the angles is always 180 degrees. If the right triangle is isosceles, the two equal angles are 45 degrees because you can only have one angle equal to 90 degrees. Again, we give you this information so that you can calculate roof lines. Okay, attic space, attic volume is extremely important. A scalene triangle has no two equal sides and therefore no two equal angles. Okay, a lot of houses you see this. You have this is the front, the left side of this is the front of the house, the right side of this is the back of the house. Makes the house look bigger from the front of the road. It's a sales technique. You have a higher peaked roof in the front, and then you have a gently sloping roof in the back. We have to be able to figure out the volume of this. That's why we're doing this. Two triangles that have the exact same angles are said to be similar triangle. They have the same basic shape, but may be of different scale or size. The sides between similar triangles are proportional. One of the triangles may appear if it grew or shrank. So again, similar triangles. Again, something we see on a lot of construction. Think about a house that has a garage that's sort of sitting to the side of it, and the roof has dropped down a little bit from the rest of the house over that garage. Could be a similar triangle if the roof comes together, but it appears as it grew or shrank. This is an example of a similar triangle. Same angles, but the size is different. Okay, the length of these lines is different. That's a similar triangle. In right triangles, one angle is always 90 degrees. The other two are always acute. The side opposite the right angle is hypotenuse. Okay, and then you have a leg and a leg. Trigonometric functions, and I'm not going to go heavily into this because it really doesn't matter for what we're doing, but you have a thing called the Pythagorean theorem. Okay, it's used to calculate the values of the sides, length, and acute angles. Okay, I'm never going to expect you to do this other than to be able to find the area of a space. Okay, there's 6 trigonometric functions that occasionally you see in design manuals. Okay, and this is why it's important. I just want you to know what they are so you can recognize them. Okay, because most often this part is done by computers, but you do have to be able to recognize them. There's trigonometric functions: sine, cosine, tangent, cosecant, secant, and tangent. Okay, we're only worried about 3 of these: the sine, cosine, tangent. Okay, each of these functions is a different ratio of the size of a right triangle for a given angle. Here on the slides is used to represent a generalized angle. You are going to see this on blueprints. Okay, that just means it's an angle. It's used like a variable. Angles are commonly symbolized by Greek letters. I don't know why they do that. They could just put angle or degree, but someone decided to mix letters and numbers together and it just makes a mess. But angles are commonly symbolized by Greek letters. Architects love this stuff, so I just need you to be aware of what they stand for. The terms opposite, side, and adjacent sides are the keys of solving right triangles. To explain these terms, the angles are labeled A, B, and C, and the sides are labeled A, B, and C. Okay, so we have our long side, which is hypotenuse. It's across from the right triangle. Then we have an opposite and an adjacent. The opposite side is the side across from angle the theta, okay? So it's the side across from your top angle. The adjacent side is the side between the right angle and your top angle. Okay? And this is, again, this is more just for your information. So the adjacent side you can also say is the side above the right angle across from a hypotenuse. Okay, and the adjacent side of angle A is side A. Remembering the trigonometric functions are the ratios of the sides of a right triangle for a given angle, they can be written as formulas. The sine, cosine, and tangent of an angle is equal to the ratio. If the angle and side are unknown, with the help of the other formulas, an unknown side can be found. Also, if the ratio is unknown, the angle can be found and the angle can be determined. Keep in mind, everything adds up to 180 degrees. That's the key for this whole thing. Everything adds up to 180 degrees. Therefore, after finding one angle, the other angle can be found using subtraction. We know we have a right triangle. That's 90 degrees. We just have to find the other angle. Knowing this, the right angle can be found. Okay, and again, I am never going to ask you to do these Okay, I just need you to be aware that they exist. So there is a function formula. Okay, so if you know two of these measurements, you can find the angles. Okay, so if you know the opposite leg and the side and the hypotenuse length, you can find the angles. Okay, because you know this angle is 90 degrees. So all you're doing is trying to find this angle. And then you can subtract. You can add these together, 90 plus whatever, and subtract it from 180, and that's how you find that angle. That's the important thing here, is that you're able to find the lengths and the angles. Again, a lot of times measurements does this for you, but sometimes on charts you just have to know it. Okay? Basically, this whole thing, the Pythagorean theorem, is basically a relationship of the three sides of a right triangle. The theorem states that the square of the hypotenuse is equal to the sum of the squares of the other side. Again, just know that this exists. This is the theorem. Okay, A2, which is this bottom side, plus B2 to the second power, okay, you take this number, you square it, equals C2. Okay, so once you find all three lengths, okay, you can find your angles. Where C is the hypotenuse and A and B are the other sides, you have to use your square root, because once I add those squares together, to get C, I have to use a square root function. Okay, so in this situation, someone has measured a single angle, or we know, okay, that B, this angle up here, is 90 degrees minus 53 degrees. That gives us an angle up here of 37 degrees. Okay? So again, all adds up to 180. So if I know 90, okay, you can subtract it all out. 90 degrees minus A is 53. Okay? Then we have our solution for B is 37, because at 37 and 53 and 90 will all add up to 180. And since I've totally put every one of you to sleep, fortunately, that's the end of the slides on that one. Okay? Any questions other than, other than how this is, then do I need to know the theorem? No, I'm never going to ask you to do it. Any other questions?
Not a question, but a concern. Well, not a concern, but the lab, this lobby, men's room, the slide you're on right now is completely different than in our assignments, lab 10.
I don't think I opened this. I don't think I opened it yet. It's going to be
we have lab 7 and lab 10 on there available for great. Well,
hang on.
But
we can solve that problem real fast. Hang on. Of course, my system's going to be slow right now. Lab. Okay, it was supposed to be that one. Let me just make sure it's the correct one in here. Yeah, okay. What was lab 10? What is lab 10? I'm going to go into it anyways, but what was lab 10? Okay, yeah, you guys can't do Lab 10 yet. Did anybody submit that yet?
No, I think it was just made available this morning.
Okay, I just want to make sure no one submitted it. I am going to pull it off of there for now. We haven't talked about everything you need to do Lab 10. So, the one I just talked about is now available there. Thank you for bringing that to my attention. Appreciate it. Okay. Now, since I've totally put everyone to sleep with that one, let's talk about more from an HVAC design standpoint. Okay. This is all based on Chapter 27, what I'm going to talk about now. Okay, it's all based on Chapter 27. It all has to do with things that are going to affect your design, because that's really where we want to go. Okay, we want to talk about what all is going to go into a building design. We're going to talk about blueprints starting next week, but eventually the goal is that you'll be able to design the air conditioning system for a building. Okay, you're going to be able to design the cooling system for a building, possibly the heating system for a building, and you're going to be able to also take a look at the ductwork and how the ductwork has to be placed. That's our whole goal for this. Okay, when you go in the field, we want you to have an understanding of proper system design and the way it should be done from the way it's not done. Okay, let me ask a question. Is the climate the same in the York area versus, let's say, upstate New York?
No.
Negative, that's correct. Is the climate the same between York and possibly here in Florida, Tampa, Florida?
No, not at all.
Okay. Biggest differences between the three areas that I've talked about is going to be
humidity,
low temperatures, high temperatures, and humidity. Okay, wind may be the same, but the biggest difference is going to be the temperature, okay, and the humidity. Now, there's a slight difference in atmospheric pressure because you guys are much higher on sea level, and so is like Albany, New York is even higher on sea level than where I'm at, which is basically at sea level. Okay, so temperature and moisture are going to be your two biggest changes. Atmospheric pressure, it's a little change, but it's not enough to make a decision. What about, can you tell me that the wind velocity is always the different or the same in, let's say, where the campus is at York to where you live? Is the wind going to be the same all the time?
No.
No, it's going to change from location to location. Okay, the wind velocity is never stable. Okay, I live on a ridge that's the highest point in the state of Florida. Do I always have a little bit of wind? Yeah, but it's going to change direction. At your house, at the campus, it's going to change direction. So the wind velocity is not a stable thing that we always know is going to be different. So when we're talking about climate, we're talking about the outdoor long weather trends. Okay, when we're talking about outdoor climate, outdoor long weather trends. When we're talking about the climate in enclosed spaces, and you're going to hear me refer to conditioned space, it's going to be your indoor conditions as normally maintained. The climate in your house is very much different than the climate you might find in the HVAC shop on campus. It's going to be a different climate because in your home, you're really looking for a lot of comfort. In the HVAC shop on the campus, we're looking for air exchange, okay, because there's some laws that apply here. Okay, we're looking for outdoor ventilation as well as some comfort, but I need to move a lot of air in and out of those spaces. Okay, equivalent temperature is another trend we have to worry about. I talked about this yesterday when I talked about the comfort zone. Okay, how warm the combination of temperature and humidity feels to occupants. And this is the average person. Okay, so basically what you're looking at here, and this is in your reading material as well, you have your temperatures on the left-hand side of this chart. You have your relative humidity here on the bottom. Okay? So let's say I have an 80-degree day with a 10% relative humidity. It's going to feel like 67, right around the 67 degrees. Okay, because it's dry. This is like out in Arizona, New Mexico. It's dry. As your sweat evaporates off your body, it cools you. So you could actually feel cold on an 80-degree day with under a 10% humidity. If I come up to 50% humidity, which is average for a summertime area, and I go to 80 degrees, okay, 50% humidity, I could still feel a little cold because the relative or equivalent temperature is about 71, 75 degrees. Okay, if I stay at that 80 degrees and start moving up to like a 90% relative humidity, okay, I am now borderlining between 80 degrees equivalent temperature and 76 degrees. People tend to start feeling hot and sticky in this environment because the water's not evaporating off your body. The moisture's not evaporating off your skin. The shaded areas on this picture, and again, this is a picture that is in your chapter, and I think there's a review question that goes against this. The shaded picture is the human comfort range. This is what the average person is comfortable in, is the shaded diagrams here. So in the summer months, we need our indoor environment to be within a shaded picture, within the shaded area here. In the winter months, we also need to heat and humidify our indoor environment to be within the shaded marks. Okay, many people keep their houses at 70 degrees in the winter months, 70 degrees according to the thermostat. Okay, people can be cold and uncomfortable if your relative humidity drops down to 30%, which is actually a lot of times what we find in heating season, okay, because it's going to feel a lot drier. There's less moisture in the air. In the summer months, I can be spending a lot of money to cool my house to 75 degrees, but if my humidity is too high, it's still going to feel warm, and people are going to have the tendency to continue to turn down that thermostat and use a lot more power. Okay, so equivalent temperatures is basically what it feels like to the person in the house. So again, take a look at the environment you're sitting in right now. What is the humidity? What's your thermostat set for? And what's the actual temperature? And are people feeling hot or cold in this environment? Because it might be outside of its comfort zone. Now, again, a word of warning on this. As soon as you hit 50% relative humidity and up, you have a tendency to grow mold. Okay? So you really have to look at this humidity. Is it worth going over 50% humidity, or is it worth adjusting the temperature? If I had people in a building with asthma and other sensitivities to mold, I would not want to go over 50% humidity because I wouldn't want to take the chance that something somewhere, no matter how clean you keep the house, is going to grow mold. If I have people also with asthma, do I want to go too low on relative humidity? Because again, too dry dries out their lungs and their airways. If I have a person on oxygen, let's say I have an elderly person in the house that has to have the supplemental oxygen, do I want the relative humidity too low? No, I don't. But also, do I want to go too high? So I want to get as close to that 50% relative humidity line, but never go over it. Does that make sense? Any questions on that?
Unclear.
Okay. So air conditioning, according to ASHRAE, which is the Air Conditioning Engineers Association, it's the process of treating air so to control its temperature, humidity, cleanliness, and distribution to meet the requirements of the conditioned space. Okay, most of what we talk about when we talk about air conditioning and heating is temperature. We don't often talk about humidity unless we're talking about what the coils of air conditioning and refrigeration systems are doing. We rarely talk about cleanliness, and we rarely think about distribution. I know some technicians who've been in the field for 20 years, and they don't take a look at the cleanliness and the distribution when they're dealing with occupant comfort issues. There's another piece that more and more people are starting to look at here that still hasn't been added to the definition, but we want to keep it in mind. That's noise. For some reason, over the last 15 years, people have become a lot more sensitive to noises that their air conditioning system makes, whether or not it's a duct banging or a blower motor that they hear or a valve opening and closing. In the dead of night, people have become very sensitive to these noises. And I think there's a nervousness about, okay, is that noise my air conditioning system or someone trying to get in the house? Okay, but people have become very sensitive to noises. I suspect ASHRAE is going to update this definition to include noise. So we use automatic controls for temperature and humidity. We use air filtering equipment. And use of air conditioning is basically for occupant comfort in a home or building, or we use it for complete control over manufacturing processes and materials. I'm trying to get into a local manufacturer here to get you some, at least pictures and video of their air conditioning and their treatment of the air quality in the building. I'm having problems getting in because of the coronavirus issue right now, and I'm having problems getting in there to take pictures. I'm trying to get one of their mechanical guys to do it for me because I think it's important to show you the air process when we're talking manufacturing. I live 1.5 miles away from the Florida Natural Orange Juice plant, and they have an awesome air quality system in there. But I'm trying to get some pictures and videos of that to share. So, air and atmosphere things. Okay, the biggest thing is, air is invisible, odorless, should be tasteless. Okay, it's a mixture of gases. Atmosphere, you talk about this more when you do your EPA, but troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Okay, I really don't care about, at this point, for this course, anything over, okay, like the troposphere, because your buildings are obviously never going to be over 10.3 miles high. So this first one is really the one that I'm worried about for this course. Okay, now this is sort of important, okay, because when we're designing systems, there's 2 or 3 things that we're really, really concerned about when we're talking about air. Okay, air includes nitrogen, oxygen, argon, carbon dioxide, hydrogen, and water. Okay, when I'm talking about building design and air quality, I could care less about the argon. Okay, it really doesn't fall into play any place. It's negligible. I could care less about it. I am really concerned about the nitrogen. I'm concerned about the oxygen. I'm concerned about carbon dioxide, and I'm concerned about water. Okay, those are the main parts of air that's in the home that I'm concerned about in terms of air quality. Now, do I also have to be worried about dust with filtration? Yeah, I need to be worried about dust. But in terms of air quality, I'm really concerned about the nitrogen, oxygen, carbon dioxide, and the water, okay? Hydrogen, we really don't worry that much about it in the average environment, maybe in manufacturing processes. Why am I worried about carbon dioxide? Anybody want to throw something out there? Why am I worried about carbon dioxide?
Can kill you.
In large quantities, you're right, but don't get that confused with carbon monoxide, which is exhaust gas. Okay, carbon dioxide, yeah, if it's in extremely large quantities, it will make you feel sleepy eventually to the point you'll stop breathing. But carbon monoxide is like a furnace leaking or a vent pipe leaking. Carbon dioxide is what you're breathing out. Okay, it's what you're actually putting out. As your body's consuming oxygen, you're putting carbon dioxide out. Okay, I can measure carbon dioxide in the air, and I can open and close outside air intakes for air exchange based on the carbon dioxide in the building. So the carbon dioxide I'm very concerned about because I can measure that. That is a measurement of my indoor air quality, especially in commercial buildings. Okay, water is basically humidity. I'm concerned about that too because too much water in the air, I grow mold. Too little water in the air, people start having nosebleeds and feel uncomfortable. So again, those are my two variables that I'm really worried about. The rest of them, know that they're there. Air has physical properties. We talked yesterday about weight, okay, but air has a lot of physical properties. It has pressure. It's the air pressure due to the weight of the air above the earth. As you go up higher, like in the Rockies, your pressure is going to go down. As you go towards sea level, there's more air above you, so the pressure is going to go up. Air has mass. Okay, air, even though it's invisible, is a substance. It has mass. It has density. Okay, more humid air is more dense. Cooled air has a greater density. That's why cold air falls and hot air rises. The density of the air, how heavy it is, changes. Air has temperature, as we know. We've been talking about that. Air has humidity. Okay, it has a presence of moisture or water vapor in the air. Warm air holds more moisture than cold air. Humidity affects the rate of evaporation of moisture. Okay? Relative humidity, it's the amount of moisture in an air sample compared to the total moisture of completely saturated. In other words, you take the moisture in an air sample and you compare it to the content of completely saturated air. In other words, if you add any more moisture, it's going to start raining. You can see this on the psychrometric chart with the curved lines. It's stated always as a percentage. Dew point. The dew point is the temperature below which water vapor in the air starts to condense. It's the temperature at which air has 100% relative humidity. And again, dew point uses, on the psychrometric chart, uses the same scale as the wet bulb temperature, but instead of going over at an angle, you're going straight across. Okay, and this chart over here just gives you, this is also in your book in chapter 27. It gives you some guidelines here, okay, based on 70-degree air and 80-degree air. Humidity measurements are done with a hygrometer, okay? The people with the newer tools have a little yellow tool in your toolkit. It's a hygrometer measurement. Those with the older toolkits, you do have to take a wet dry bulb thermometer reading, and you can come up with the relative humidity. Okay, hygrometer measurements, relative humidity, temperature, dew point, wet bulb temperature. Same as that little yellow tools. Okay, we use measurements over time quite a lot when we're figuring out average climates in an area. I've had to occasionally leave my psychrometric probe, the one that I showed you guys when I was up there, in an area for a couple days and use the charting function of the application to figure out what's happening. Because when I'm on a site looking at like a mold problem, I may not be seeing the whole picture. Something might be changing over time. So I go look at that temperature and humidity over time. The graphs on that chart are very helpful. Decadent is another word I do need you to know. A decadent absorbs moisture. Okay? A decadent is sort of like those, you open up the electronic packages or a new pair of sneakers, you have the little bag of stuff in there that says don't feed this to your kids or pets or anything like that. It has silica gel in it. That's a decadent. It absorbs moisture. It keeps things cold or dry. We can use these in dehumidifiers. We can use these and we can spin them around. So we have one side of it facing the indoor airstream And then we have another side of it facing an outlet where we blow air to the outside environment and we dry those things off. Okay, so decadents can hold and release moisture depending on airflow. Humidity controls, in the winter, we add moisture to dry air. In the summer, we remove moisture. Now, your air conditioning by itself is a dehumidifier. It will remove moisture from the air. Believe it or not, that's one of the primary purposes of air conditioning, is to remove moisture. Okay, in the winter, we have to use a humidifier to add moisture to the dry air. Basically, we either use steam or we throw water droplets into the airstream or something to add moisture into the air. Air temperature, again, an air property. Common scales are Fahrenheit, Celsius, and Kelvin. We have a wet bulb temperature and a dry bulb temperature. Again, wet bulb temperature, we put some saturated material over the end of the thermometer, and then we move it around in the air. It can't just be standing still. We have to move air across that wet bulb. Okay? One of the things we used to use before we had all these electronic tools that we now have to do our wet bulb, dry bulb temperatures, okay, we used to use our meter leads with the old shoelaces, okay, cut a piece off an old cotton shoelace, put it over the end of it, hold it on there, and then wet that down. And that's actually, the cotton shoelaces are a great wick for wet bulb temperature. I still know a lot of the technicians that prefer to use this approach than any electronic tool. With most electronic tools, as the batteries get weaker, okay, the tool is not going to give you the right reading. You're going to find that on your meters as well eventually. As the batteries wear out, the readings change. Okay, so as soon as you have a low battery light on something, the readings change. Okay, so we have wet and dry bulb temperatures. You see this a lot on weather stations, okay, degree days. And this is very used in design, okay. A degree day, it indicates the heating or cooling need for a region, okay. Again, I named 3 parts of the country: Albany, New York, York, Pennsylvania, Tampa, Florida, okay. We have different degree days in these different areas. Albany, New York, your heating degree days, which is the degree days, okay, over, basically under 65 degrees, is a heating degree day, okay? If it's over, or 18 degrees Celsius, okay? If it's above 65 degrees, it's a cooling degree day, okay? In Albany, New York, I'm going to have more heating degree days than cooling degree days. Okay, in York, Pennsylvania, I don't know. You guys are probably about the same if we use the 65 degrees. Okay, possibly a little bit more heating degree, but you're a little closer. In Tampa, Florida, I have way more heating or cooling degree days than heating degree days. Okay, I'm running the air conditioning and have been probably, I think I've turned it off for probably 6 days this year. So we have...
You can stop right there with that crap.
Sorry.
Jealous.
Sorry. I do take that opportunity to rub it in occasionally. Okay, so the psychrometric properties of air is what we're talking about with the science of studying the different properties of air. I don't need you guys to know the sciences. I need you guys to know how to use it. We need to allow design of the systems to control the environmental conditions. We have 2 different psychrometers. When we get back on campus, we'll show you the sling psychrometer. That's what this is over here. Okay, this is designed so you hold the handle and you actually swing the top portion around in circles. Okay, you have the electronic psychrometer, which you guys have, again, those yellow ones in your toolkits. And for those who don't have the yellow ones, I'm going to try to find the link to the supplier, and I think there's like a 20% off coupon or something like that. I can't add them to your toolkits because it's what you purchased originally when you signed up, but I can definitely try to make it available to you if you want it. Okay, it's not a requirement because there's other tools out there to do it, like the piece of paper towel over the meter, but I definitely want to make it available to you guys if you want it, and our tool supplier will do that. And I think there's a 20% off coupon or a 30 or something like that out right now. Psychrometric chart, I spent a lot of time on this yesterday. It's a graph of temperature and humidity conditions. Dry bulb, wet bulb, specific humidity levels, relative humidity levels, volumes, enthalpy, and sensible heat ratio. Dry bulb, line straight up from the bottom. Okay, they're in red on this chart. Between 20 degrees and up to 110 degrees. Okay, I really wouldn't want to be outside those lines myself, so I think those are fair. That's a fair range. Wet bulb temperatures. They're the angled lines coming down from the curved side. They're in red on this picture. Again, from 20 degrees all the way up, okay, to roughly around that 110 or whatever degrees up there, or 106, I think it is. Okay, some charts go further. They do have high temperature ones and they have low temperature ones. But most often for residential and commercial design, these are the ranges you're in. Okay, constant specific humidity, that's your grains of moisture. Again, the scale is on the right. It's going to say grains per pound most often. Okay. That's per pound of air because air has weight. There's another version too that I showed you on the ACA chart yesterday that has this slightly different. But, okay, this chart is moisture grains per pound. From basically you're reading the scale on the right and you're going to the left. Relative humidity, the curved lines. Okay, relative humidity is the curved lines. And usually every other one of these is actually labeled. Constant specific volume. That's what's your cubic feet of air, okay, per pound. Okay, so it's CF per pound. And if you look closely at the numbers, again, this is in your book, okay, it will tell you. Now, I care about this because I care about how many pounds of air am I moving. It was a blower motor or through ductwork. Enthalpy and sensible heat ratio, you just extend the various lines and you can find my enthalpy, which is how much heat is totally in the air, including moisture, and how much of that, what percentage of that, or what the ratio is of sensible heat. Remember, sensible heat is heat I can measure, heat I can take out and put in without changing the moisture content of air. So that becomes pretty important when we talk about humidification and dehumidification. To read a psychrometric chart, I need to know 2 points. Okay, if I know 2 numbers, okay, 2 lines that cross, I can come up with every other value on this chart. So if I know relative humidity, and if I know dry bulb temperature, I can tell you what the wet bulb is. I can tell you what the enthalpy is. Most often, the 2 numbers we use are the wet bulb and dry bulb temperatures. Those are the easiest to get. Okay, it's the most accurate. So once you know any 2 numbers, you can find the other values. And in terms of things that end up between lines, okay, if it's between lines, you just have to come to the closest one. Okay, like you have a sort of pink line at the right of this, you have a yellow line at the left, your point is exactly in the middle, and either give a number of 14 or pick one that's closer. Okay, for your purposes, that's going to really be the way to do it. I mean, if I were teaching an engineering class, I would be thinking, okay, yeah, let's get this more exact and use a formula. I'm not worried about that. HVAC processes are modeled at key stages on this chart. You have a heating process, you have a cooling process, you have a humidification process, and you have a dehumidification. All we're doing here is, remember, yesterday I put a cooling process up there. I said, okay, here's my return air, here's my supply air. What is the process? What are we having to do with that air to get to those points? It provides a visual model of the change. Comfort conditions. This is the same chart I drew up there yesterday. They just chose to follow the curved lines, which I didn't really do because I can't draw curved lines very well on the tool that I have. Comfort ranges vary from season to season. In the summer, we're talking 72-degree dry bulb and 97% relative humidity to 87-degree and 23% relative humidity. Those are our comfort ranges. Winter, it changes a little bit. Okay, we want to be between 66 degrees, 70% relative humidity, or 80 degrees, 20% relative humidity. Now again, 70% relative humidity, what's going to happen in that house? Anybody? 70% relative humidity. What's possible happening?
It's going to be very dry. Wet.
It's too wet. It's over 50. So what could I be taking a chance of happening?
Mold.
Mold. Could grow mold. The highest comfort level is if your skin is at 91 degrees. If you go over 91 degrees, no matter what you do, okay, you are going to be uncomfortable. And again, there's a comfort index. This is in your book. I think some of your, one of your review questions, one of the chapter review questions takes a look at this chart. But the reality is, if you stay within those comfort ranges, okay, you're okay. Now, if you have a homeowner that starts complaining about being outside those comfort range, or starts complaining that they're too hot, too dry, too cold, or if you live with somebody that's always outside those comfort ranges, you need to take a look at the humidity and temperature combinations. It's very possible that they're more sensitive to being outside that comfort range. Probably not the best thing to say when a lot of you have me on speaker right now with other people around, but okay. Wind makes a difference. There's a Beaufort scale of wind velocity. Wind affects the efficiency of heating systems. A building's calculated heat load, in other words, how much heat we have to provide, should include a maximum wind velocity for the area. We're going to go into that as we start talking about the design. We have a wind chill index. It describes the combined effect of temperature and wind speed. You see this on the news all the time. What's the wind chill? They call it the feels-like temperature a lot of times. Okay, there's a wind chill chart put out by NOAA, okay, that you might have seen before. Okay, there's also a formula you can use if you don't like using charts and want to do things the hard way. I like using charts. So if my wind is 10 miles an hour, it's relatively calm, and my actual temperature is, let's say 30 degrees, it's going to feel like 21 degrees. And I wish I could draw on this, but always have a problem with that on this one. But again, you go 10 mile per hour on the left-hand column, 30 degree from the top, you're going to feel like 21 degrees. Okay, and it just gets more bad news from there all the way down to the right-hand side, which I think would be the Arctic Circle. Okay, now the colors are on here is how long would it take for you to get frostbite on unexposed skin? 30 minutes, 10 minutes, or 5 minutes? Okay, again, the bad news just goes from the top left down to the bottom right. And again, there is a formula for this. This is what your gauge, this is what electronic tools actually use. They take the measurements, they do the math. But that's the wind chill chart. Air velocity measurements. Okay, outside air velocity is usually measured in miles an hour, or if you're dealing with marine, it's measured in knots. Okay, indoor air velocity. This one is extremely important. Feet per minute. How fast the air is moving in ductwork is talked about feet per minute, or FPM. If I had to remember anything, I'd remember that one. That is pretty important. Now, volume of air, as I was talking about yesterday, is cubic feet per minute, CFM, cubic feet per minute. The indoor air volume for air conditioning is based on the size of the air conditioning system. Okay, you have to move a certain amount of air per ton of air conditioning. The magic number is 400. Per ton of air conditioning, I have to move 400 CFM of air. But it has to be at the proper speed as well. So think about your own comfort. If I am blowing air out of a register at a temperature that's maybe 55 degrees coming out of that register, and if you're in the airstream sitting there working on something, sitting there eating, are you going to feel comfortable if that air is fast or slow?
Depends, don't it?
Well, 55 degrees, that air is blowing down at you as you're sitting there.
Cold.
Slow, I believe.
You said 55 degrees, right?
Yeah, 55 degrees.
55 degrees and it's blowing across you, you're going to be cold.
Yeah, most people will feel cold. Now again, if the room temperature, and I know what some of you are thinking, if the room temperature is like 100 degrees, you're going to enjoy that 55 degree air. But under normal circumstances, if that air is moving very fast across you, at 55 degrees, you are going to be cold. Okay, and if you're not cold, someone else in your household is going to slap you. So just be aware of that when you're placing ductwork and when you're thinking about the rate of the air. Now, if I blow 55 degree air out of a register and I don't blow it on the occupants, if I sort of disperse it across the ceiling of a room and let it fall on itself, would that be a slightly different feeling than the air blowing out of a register directly at you?
Of course, yes.
Yeah, so which one would you or your customers prefer?
The one coming from the ceiling.
Yeah, the disbursement. So if this all has to do with the air velocity. How fast is the air blowing out of those registers? What else does very fast moving air have that might be uncomfortable to people around it? If I'm blowing very fast moving air out of a register, what else could cause a problem?
Dust?
Well, dust is one thing, but what about sound?
Sound?
Yeah, sound. You don't want somebody to be hearing the air moving all the time. In the perfect indoor environment, in the perfect design of a heating or air conditioning system, we want that to be invisible. We do not want people to be constantly hearing the air moving. We want it to be invisible. Okay, we want it to be heating and cooling without them realizing it's actually doing it. Okay, so if I move air too fast, we're going to have sound issues. But then again, if I move air too slow, it's going to take me longer to cool the space. So there's some guidelines we're going to talk about the rate of air movement. And we're going to talk about that when we talk about air distribution. Okay, we can measure air velocity. We use a tool called an anemometer. I think I showed it to you the other day when I was up there. I'm pretty sure when I was showing off my Testo kits, I showed you the little one that had it looked like a fan inside the tool. Okay, it's an anemometer. It actually blows, as the air blows across it, it starts speeding up those fan blades. The other one that I use, that we all use, is the manometer. Okay, it measures air pressures. Okay, and again, you use velocity pressure to calculate velocity. We're going to go more into this when we talk about pressure, so I'm not really going to go over this right now. Okay, we're going to go into this, how this works more in ductwork. Ventilation is extremely important, especially when we have situations like the reason we're doing this online versus doing it in the classroom. We got to change the air in the building. Someone that I took a class from up at Northeastern University once said something very important. The solution to pollution is dilution. Again, that's the solution to pollution is dilution. In other words, if we have a polluted indoor environment, we have people breathing, we have cooking going on, we have germs, we have whatever. The more outside cleaner air we bring in, we all know that air isn't totally clean, but the more outside air we bring in, the better the indoor environment is going to be. Okay, so that's what we do ventilation for. That's the V in HVAC. In the winter, we know that by itself, heated air rises. So by putting vents to the outside environment in certain places, we can naturally ventilate a building. Okay, this happens a lot in manufacturing facilities. We put vents at the top, near the roof line. We put intakes at the lower levels. Okay? If any of you, I think a few of you work on some horse farms and stuff like that, you'll see this in some of the barns. Okay, they put vents near the top, and they can put intakes near the bottom where we can create air patterns. Okay, in the summer, cold air flows downward. It's replaced by warm air at the upper level. So we close those usually floor vents at the in the summertime, and we have to do something else because that just doesn't work well in the summer. But in the winter, we can ventilate a building just by using the heat in the building. Makeup air is something that replaces the air vented out of a building. Makeup air is critical for combustion and fuel burning processes. For example, cooking, heating, or whatever with a combustible fuel. Okay? For those who've worked in restaurants, you have the grill hoods suck a tremendous amount of air out of the kitchens, okay, and it has to be replaced with makeup air. We use motorized makeup air units in most restaurant kitchens to bring in outside air. So if you take a look at these really odd-shaped houses, okay, you can see that even in a house, and you relate this to any building, we have seasonal indoor airflow. In the heating season, warm air is going to want to rise, and it's going to attempt to rise to the attic level. In other words, my lower portion of the house a lot of times is in what we call a negative pressure. And a negative pressure just means that the air pressure in this environment is lower than the surrounding air, which is the outside air. The negative pressure is going to pull in air through the walls. If you've ever in the winter months put your hand in front of an electrical outlet and you feel the cold air blowing in, okay, it's because your house is in a negative pressure and it's sucking that cold air in through any available spot. That's not a good thing. Okay, the upstairs could be in a positive pressure on a second floor, and it's pushing your air conditioned or your heated air out to the outside environment. Again, not a good thing. It's called heat loss. In the cooling season, we have the opposite effect. You might be on the second floor, the higher points of your house, and you're feeling air being pulled in, hot air being pulled in through the window frames and through the outside. Again, not a good thing. Okay, but it's less dangerous than the heating season. The heating season problem is the biggest issue over on the left-hand one, diagram A, is your furnaces and everything are on this first floor. Okay, sometimes the furnace will actually pull the air in from the vent pipe, and it can cause a carbon monoxide problem. We're going to talk more about that as we talk about design. In the cooling season, all we're dealing with here is a lot of energy loss. Usually there's nothing dangerous about this situation other than for your power bill. So if somebody could remember that I'm leaving off at slide 33, that's about as far as I'm going to go in this session. We're going to continue this conversation tomorrow. Does anybody have any questions about what I've gone over?
I have one question. We're just doing Lab 6, right?
Yeah, do Lab 6. I did make Lab 7 available. That's more for tomorrow. But worry about Lab 6 right now. But again, if you want... Oh, Lab 7 was the one I assigned yesterday. That was the psychrometric lookup.
Yeah, that's already finished.
Yeah. Okay, so do Lab 6, and again, those, if you look at the file numbers, they're the wrong numbers there, but do both of those and you're fine. Any other questions?
What about the discussions?
Yeah, there is a discussion board open. I need you guys to do those. And I'm not going to, the one from yesterday about the windows, everybody please go post a better answer in that. If you didn't give me a good answer, if you gave me a little tiny short answer or something that's totally off the wall, please go post a better answer in that. I do need to know, the discussion board is the only way I really know that you have an understanding of what we talked about. That's the only, because I can't see you guys. I don't know if I have a glazed over look in the eyes, okay, that I normally can see in the classroom. But I need those discussion boards just to make sure we're on the right track. Okay, so please do the discussions. Any other questions? Okay, I think that's all that I have. What? Go ahead.
I've got a question. The homework 20, the 27, chapter 27, that's for today too?
What is the due date on that? I put a due date on that. I don't think it was today. Yeah, March, I said the 27th, so that's Friday. As long as you get it turned in sometime by midnight on Friday night, you're fine.
Okay, thank you.
Does that work?
Yes.
Okay, yeah. Again, just watch over on the right-hand side. I do use due dates. I do try to make this as much as possible so you guys can see it. So that's all I have for today. If you have any questions that you want to ask me separately, you have my email, you have my phone number. I answer text messages. And I'll return calls if I'm on another call. If you leave me a voicemail, just give me a good time to reach you. I will make this recording available as soon as I get the link from it. It takes it a couple hours to process these days. So thank you. You all have a great afternoon, and I look forward to reading some discussion board posts.